Greetings, Spartan fans. Welcome to Polar Equations and Graphs Part 2. You will need several polar graphs for today's lesson. When you graph a line, there are several forms of a line. There's point-slope form, standard form, slope-intercept form. When you look at parabolas, there's standard form and vertex form. So they come in all different types of equations. And the same is true for polar equations and graphs. And we're going to look at several of those in today's lesson. First, and we're going to do some French, if I pronounce things correctly. I know who thought that French would be involved in math, but it is. Okay, so the first type of equation we're going to look at is, I wrote y, and that should be an r. R is equal to a plus or minus a times the cosine of theta, as well as r equals a plus or minus a times the sine of theta. Okay, equations in this form create a shape called a cardioid. And cardio is pertains to the heart. And so these graphs are going to look something like a heart. And I'm going to draw a beautiful heart, generically speaking. And I'm going to refer to this point right here quite a bit. So you'll notice that what's being added is the same as the coefficient, and that's going to matter when we change these values. Are they always the same? What does that do to the actual shape? The cosine is related to the x-axis. So for a long time, when we've been doing the cosine, it always refers to x, and the sine always refers to y. If it is a cosine equation, this is going to have x-axis symmetry. And that's also referred to as the pole. Did I spell that right? X-axis symmetry? I think I spelled it right. This is also referred to as the pole axis. And along those same lines, sine is related to y. So this is going to have y-axis symmetry. And this is going to save us a lot of time when it comes to plugging in points, etc. And the y-axis symmetry doesn't have a fancy name, that we just say it's symmetric to pi over 2, which is the y-axis. So in case you were wondering, the y-axis, we just call it pi over 2, but the x-axis is called the pole. Okay. I'm going to go ahead and graph one of these, and then we'll talk more about this cardioid and the point. So let's look at how about r equals about 2 minus 2 sine theta. Okay, so even the 2 is being subtracted, we consider a to be 2 for both of these. So even though the radius doesn't say -2, which of course doesn't make any sense that it would be negative, these are a is considered to be 2. It's a sine curve. I would right away determine that this has y-axis, or sorry, y-axis symmetry. I think that's going to be very helpful. Okay, and let's just plug in some points like like you used to do when you would first learn how to graph something. So let's just make a quick little chart. And I tend to plug in, when you're graphing a line or whatever, you plug in -2, -1, 0, 1, and 2. I tend to plug in 0, pi over 2, pi, and 3 pi over 2. You can plug in whatever you want. So here's my theta, and that's going to give me my r. Okay, so if you plug in 0, the sine of 0 is 0, times 2 is 0, 2 minus 0 is 2. Pi over 2, the sine of pi over 2 is 1. 2 times 1 is 2, 2 minus 2 is 0. Plug in pi, we're not going to really have to do that. Well, I mean, I'm going to, but I'll show you why in a minute, why that's not necessary. The sine of pi is 0. 2 times 0 is 0. 2 minus 0 is 2. And 3 pi over 2, the sine of 3 pi over 2 is negative 1. 2 times negative 1 is negative 2. 2 minus negative 2 is 4. All right, and then let's plot our points. Theta is 0, the radius is 2, 1, 2. Pi over 2, 0, that's here. Pi 2, pi. And 3 pi over 2 for 1, 2, 3. This has y-axis symmetry, means if you reflect it over the y-axis, the point at 0 should be the same as the point at pi. All right, well, I'm going to need a couple other points to see what this looks like. I don't require that you plug in many, like maybe more than 2 points. Let's plug in pi over 4. The sine of pi over 4 is root 2 over 2. Which is nice because then when you multiply it by 2, you can reduce out. So if you plug in pi over 4, we may have to use our calculator to approximate this. This is going to be 2 minus 2, 2 minus 2. The sine of pi over 4 is root 2 over 2, which then becomes 2 minus root 2. So whatever, like negative half maybe. More like positive 1. It's positive 1/2-ish. Okay, so pi over 4, 45 degrees. 1, 2, 3, 4. It's like there on my graph. And it's about 1/2. Oh, that's really hard to graph. So, I mean, again, total approximation. Ish. Reflected over. I don't need to plug in another point. If pi over 4 is at approximately 1/2, reflect it, that means 3 pi over 4 is going to be at approximately 1/2, which is, there, give or take. Let's plug in a point in either the third or the fourth quadrant. Plug in a point, either the third or the fourth quadrant. I want the 2's to reduce out. So if I could find an angle whose sine is root 3 over 2, then times this 2, they would reduce out, and that would be nice. So who has a sine of root 3 over 2? It would be 60 degrees, which would be 4 pi over 3. Which is then going to be the same as 5 pi over 3 because I can reflect it over. So the sine of 4 pi over 3 is negative root 3 over 2, I believe. Yeah. Reduce, so this becomes 2 plus root 3. Got my handy dandy calculator here. 3.7-ish. For graphing purposes, you're going to have to approximate. So 3.7, 60 degrees. 1, 2, 3, 4, 5, 6. This is 4, so it's there-ish. 1, 2, 3, 4, 5, 6. It's there-ish. Knowing that it's a heart is going to be super helpful. So I'm going to sketch this first with pencil because my drawing abilities are pretty poor. As you can see, this does not look great. It's heart-esque. So it's a cardioid. It is heart-esque. It's not this perfect heart. This is, for our intents and purposes, a very good graph. How many points do you need? You should have, like I said, the four main coordinates, which are 0, pi over 2, pi, 3, pi over 2. So you should have these. And then you should plug in at least 2 other points. So this is your heart. Notice that it is symmetric over the y-axis. So let's look at graphs where the value that's being added and the coefficient on sign are different. And this is where our French is going to come into play. All right. We have what are called limisons. If you're French speaking, I apologize now. They are referred to as limisons, and they have an apostrophe, or I think that's not called an apostrophe, an accent mark in their name. So you have what is known as it looks like limicon. That is not what it's called. It's called a limison. And hold on, I'm looking up where is the accent mark. The accent mark is, oh, I can't draw it. It's like underneath the C. My apologies. So you have a limison with a loop, with an inner loop. And when I show you an example, essentially it's a heart that has a loop. And then you have a limison without a loop. Okay, so the limison with the loop is of the form R equals A plus B cosine, and then of course A plus B sine. They look the same. Without the loop, same equations. Okay. For with the loop, A is less than B. Of course, it is greater than 0. And without the loop, B is less than A. I don't memorize. I plot like 2 or 3 points, and then I think you'll be able to figure it out. Okay. And again, cosine is going to have x-axis symmetry for all of these. Pole axis symmetry for all of these graphs. It's a cosine curve, x-axis symmetry, and if it's a sine curve, it has y-axis symmetry. Pole axis, pi over 2 axis. I just refer to it as x and y. Okay, so let's take a look at one of these. Let's take a look at one of these. How about R is equal to 4 plus 2 sine theta. So A is 4, B is 2. You don't have to label it. Sometimes I do. So in this case, B is less than A. So this is going to be no loop. B is less than A. So this is going to be no loop. Well, what's that look like? Essentially, this is a cardioid. All 3 of these are cardioids. The cardioid that we just did with the loop, without a loop. This is a cardioid shifted up where the point So this point of the heart is not at the origin. So the point of our cardioid was at the origin. The limison without the loop is just a shift. This is going to have y-axis symmetry. This is going to save us from having to plug in points. I don't memorize any of this. I plug in my 4 points and I say, okay, this is what it looks like. All right, so let's make a little T-chart. I'm going to plug in the 4 points, and I hope that's going to be enough to at least get me started. If it's got y-axis symmetry, then I'm not going to plug in pi. If you plug in 0, you don't get 0. That's how you know it doesn't go through the origin. When I plug in any of these points, none of them are going to be 0. That's how you know it's not a cardioid. Or it's not a cardioid through the origin. Cardioid through the origin. One of these has to be 0. Actually, any of them have to be 0. Not going to happen. There's no value of theta that you're going to plug in that's going to make R 0. Sine of 0 is 0 times 2 is 0. You get 4, which means that when you plug in pi, you also get 4. Pi over 2, 6. 3 pi over 2, you get 2. I know I did that pretty fast. Plug in the points. I think that's right. Yeah. And let's take a look at the graph. 0, 4. Be careful. When theta is 0, the radius is 4. It is not 0, 4 on the y-axis. It's on the x-axis. Find the measure of the angle. The angle is 0. Move 4 circles, 4 radii in the 0 direction. Pi over 2, and sorry, and let's just reflect that over right now because I know it has y-axis symmetry. Pi over 2, 6. 1, 2, 3, 4. Oh, shoot. Okay. I should have counted how many circles I had first. And then 3 pi over 2, 2. Okay, well, this is kind of hard to figure out right now. So I'm going to plug in a couple other points. I'm going to plug in a sine of 1/2 because when I multiply it by 2, it'll be a nice whole number. I don't have to worry about any roots. So a sine of 2 would be 30 degrees, pi over 6. Sorry, I said 2, I meant 1/2. Sine of pi over 6 is 1/2 times 2 is 1. This is 5. 30 degrees. 1, 2, 3, 4, 5, 1, 2, 3. And then when I reflect it over, so that's also going to be 5 pi over 6. Let's look at some angles maybe in the 3rd and 4th quadrant, because I don't know about you. It's hard for me to kind of see what this looks like. You'll get better at it. This would be 30 degrees in the 3rd quadrant. You can plug in anything you want. I'm specifically plugging in pi over 6 references because sine of any 30-degree reference in any of the quadrants is 1/2, and that reduces nicely with the 2. So how about 7 pi over 6? That would be -1/2, -1. This is going to be 3. 1, 2, 3. 1, 2, 3. Okay. I'm going to turn my page upside down so that I can draw a better graph. Oh, not great. Good enough. This is an upside down heart. Not the way I've drawn it, but that is a heart. And the point of the heart, instead of going to the origin, now goes through the point, whatever that is. So notice y-axis symmetry for sure. And there's another way that I look at this. Positive 2 sine theta. Positive sign is in the first and second quadrant. Plus 2 sine, that's positive sign, first and second quadrant. And if you look at this, the quote unquote bulk of this heart is in the first and second quadrant. The bulk of the heart. Some of you are like, huh? And that's okay. The majority of this graph lies in the first and second quadrant. So if it was minus 2 sine theta, this would be flipped over. So that is a limison without a loop. Let's do a cosine curve with a loop. Let's do a cosine curve with a loop. So a cosine curve with a loop means that A has to be less than B. So let's do, let's flip it around and let's do subtraction. Let's do 2 minus 4 cosine. Okay. A is less than B. So this is going to have a loop. It's helpful to know that ahead of time. This is a cosine curve, so it is going to have x-axis symmetry, pole axis symmetry. And this is a negative cosine curve. This is a negative cosine curve. Cosine, x-axis, negative quadrant 2 and 3. So whatever this is, the bulk of the graph is going to be in the second and third quadrants. Okay, so just like I did for here, I'm not going to plug in 0. I'm not going to plug them all in, because if it has x-axis symmetry, if it has x-axis symmetry, that means pi over 2, 3 pi over 2 are going to give me the same results. You can check all of these on your calculator. Make sure that you are in radians and make sure that you are in you're in polar mode. On your calculator mode, make sure that you are in polar mode. I'm in degrees from whenever I did this last, radians. And then you can check all of the graphs. Okay, theta, R. So I'm going to plug in 0, pi over 2. My pi over 2 answer is going to be the same as my 3 pi over 2 answer. Pi. Okay. If I want to avoid the awful fractions, I'm going to plug in whoever has a cosine with a denominator of 2, which is actually both 30 and 60. So let's do 30 degrees again. So pi over 6 and then 5 pi over 6, and we'll reflect those over. If you need to plug in more points, or if you're not sure about the symmetry, then plug in more, go for it, but it takes time. The cosine of 0 is 1. The cosine of 0 is 1. So 2 minus 4 is negative 2. This is a key to you. As soon as you see a result with a negative radius, it's going to be a loop. This is just a little trick. As soon as you see a negative radius, it's going to be a loop. When we graph it, I'll be clearer about that. Pi over 2, the cosine of pi over 2 is 0. So 2, that's just 2, which is going to be the same for 3 pi over 2 when I reflect it. Pi, the cosine of pi is negative 1. So this is going to be 6, I believe. Negative 1, yeah. Pi over 6, the cosine of pi over 6. I'll write it out, maybe doing it off the top of your head. Maybe I'm not, maybe I'm doing this too fast. This is 1/2. That's not right. This should be pi over 3. This should be pi over 3. The cosine of pi over 3 is 1/2. So this is 2 minus 4. 2 minus 2, this is 0. So this should be 2 pi over 3. Sorry about that. All right, let's draw a graph. Knowing the symmetry will save you a lot of time when it comes to plugging in points. Okay, so 0, -2, be careful. The angle is 0, which is the x-axis. And then instead of going to the positive radii, you move in the negative direction. It's going to be very hard for you not to put it on the negative y-axis. Pi over 2, 2. X-axis symmetry, I'm going to reflect that right over 3 pi over 2, 2. And if you don't believe me, the cosine of 3 pi over 2 is 0. 4 times 0 is 0. 2 minus 0 is actually 2. Pi, you get 6. Oh, again, I should have gone by different increments. Sorry. Pi over 3, you get 0. Pi over 3 is 60 degrees. Oh, it doesn't matter. 0 is the origin. And then can't reflect that over. When you reflect the origin, you get the origin. And then 2 pi over 3 is 4. 2 pi over 3 is 4. That's 80, 70, 60 here, I think. Yeah, and I'm going to reflect that over. Another way that you know this is going to have a loop is because you have 3 points lined up on the same axis. 3 points lined up on the same axis. That did not happen when we did a no loop with the A being greater than B. So this is another way you know that it has a loop. These are incredibly difficult for me to draw. There is a limison with a loop. So it's kind of a heart, means, excuse me, it's not a perfect heart, but it does resemble the heart, the cardioid. Then it has the loop in the middle. Notice it does have x-axis symmetry, and we didn't plug in. How many points did I plug in? 1, 2, 3, 4. I plugged in 5 points. I got 7 points on my graph. Cosine is, the cosine's negative, and so I said the bulk of the graph was going to be in the second and third quadrant, and it sure is. The question you might wonder is, how high up do I have to go here? And I'm not really picky about that. So like, does it come much further out? I think you just go with the natural flow of the graph. This is a limison with a loop. Okay, there are some other graphs as well. I'm just going to do one more. I think the video gets pretty long otherwise. Let's look at petals and lemniscates. Sounds like lemon biscuits. Lemniscates. Let's look at R equals. Okay. This is a rose with 8 petals. when the coefficient is even. So when the coefficient is even, then you have twice as many petals. And if the coefficient is odd, so a little side note, an odd coefficient, then the same number of petals. Meaning, if this was 3 times the cosine of 7 theta, it would have 7 petals. If it was 4 times the sine of 11 theta, plug these into your calculator, have fun. These are super fun. You are now able to graph flowers. Cosine, it's going to have x-axis symmetry. It's going to save us so much time. 8 petals, oh my goodness gracious. So this should have x-axis symmetry. And what I was saying in the previous problem about how the bulk of the graph is in the third quadrant, the fourth quadrant, whatever. Yeah, that doesn't pertain here. Petals are going to be in all of the quadrants. So let's just start with 0, pi over 2, whatever, but we are going to have to plug in many more values for theta in order to figure it out. Okay, so if theta is 0, we are going to get 3, I believe. 4 times 0 is 0. If this has x-axis symmetry, that doesn't help us much. When you plug in pi over 2, when you plug in pi over 2, you get 2 pi. Isn't that also 3? Uh-oh, not going to help us very much. When you plug in pi, you get 4 pi, which is the same thing as 2 pi, which is the same thing as 0, because it's, coterminal angles. This is not helping us very much. And when you plug in 3 pi over 2, I bet you can't guess what happens. When you plug in 3 pi over 2, you get 6 pi, which is the same thing as 4 pi, which is the same thing as 2 pi, which is the same thing as 0. Oh my gosh, what are we going to do? We're going to try and graph and figure it out. Everything is 3. So 0, 3, pi over 2, 3, pi, 3, 3 pi over 2, 3. Oh my goodness gracious. I'm going to have to figure out some points in between here. So cosine, let's plug in, it doesn't really matter. Let's plug in pi over 4. Plug in pi over 4, you get pi. The cosine of pi is -1, so you get -3. I believe that's right. 4 times pi over 4 is pi. Cosine of pi is, yeah, okay, so pi over 4, -3. It's there-ish. Okay, x-axis symmetry. There-ish. Oh my goodness gracious. How about we plug in 3 pi over 4? That's 3 pi. 3 pi over 4 times 4 is 3 pi. The cosine of 3 pi is -1. You also get -3. reflected over the x-axis. Okay. This is not correct. 1, 2, this should be here. This point is incorrect. This graph does indeed go through the origin. Somewhere the cosine is 0. Somewhere the cosine is 0. And that somewhere is at pi over 2 and 3 pi over 2. So which angle is that? It doesn't really matter. So, I'll show you, but so I want 4 theta to equal pi over 2, which would be pi over 8. So it doesn't really matter where pi over 8 is because the answer is 0. It doesn't really matter where pi over 8 is on my graph because if it's 0, then it's 0. All right, we got to try and get some other points in here. We know it has 8 petals. We know it has 8 petals, and so this is eventually what the graph is going to look like. So how did I know that? All right. The radius is 3, so that is going to be the tip of each petal. This is the graph, 3 cosine 4 theta. The radius is 3. That's the largest value of r that we're going to get because the largest value for the cosine is 1. Regardless of what theta is, the largest value for the cosine is going to be 1 because we're not adding or subtracting to the value. So the tip of all of these petals has to be 3. The largest value of the cosine is going to be, is 1. So r equals 3 times the cosine of 4 theta has a highest value of 3. We're not adding, 2 minus 3, 4 cosine theta. We're not going to graph those. We're not going to graph when you have something being added, subtracted, as well as a coefficient on theta. Those get pretty big. Okay, so if I've got x-axis symmetry and one of the petals goes like such, that's a reflection over the x-axis. And if one of the petals is like such, and I reflect that over the x-axis, and I have a petal here, the largest, if I reflect that over the x-axis, and then I have petal here, reflect over the x-axis. Look how pretty that is. There is a rose with 4 petals. If you would like further, there's just a big summary. I've done them for the most part, all of them, on page 583, 584. There's a big table that summarizes. with all of their proper names. This doesn't have a fancy French name. It's called a rose with a certain number of petals. Plug it into your calculator. They're pretty cool. I would also like try something fun. Y equals 2 minus 3 times the cosine of 6 theta. Try plugging in ones where there's a coefficient on theta and you're adding and subtracting. You'll see that they're pretty cool. All right, Spartan fans, that is it for today.